How's it going and welcome back. Today I'm going to walk you through how to build a human segmentation model in Tensorflow. So basically the idea is we're going to kind of build off of the previous videos where I laid out the UNet architecture, which is used for what we call semantic segmentation. So today I'm going to go ahead and walk you through how to apply that and use that model on a problem that requires such a model. So if we go ahead and take a look, we have Kaggle pulled up, and I'm at this human segmentation dataset provided by this person. So basically, if you go ahead and take a look at the data set, what we have is just pictures of people and then their annotations. So per pixel annotations of where they're at, except for these come in these JSON files. So if you go ahead and take a look at one of the JSON files, looks like we have some shapes, so we just have like the shapes, line colors, all that kind of stuff, right? So I'm going to go ahead and walk you through how to, go from having a segmentation model, and then now we have a problem. And when we have data, I'm going to walk you through how to take the data, get it in the format you need for the model and for the task, and then go ahead and train the model and then apply it to some downstream tasks, right? Maybe upload our own images and see if we can crop ourselves out of them. So let's go ahead and get started. So go ahead and click new notebook. So I'm on the dataset page. Go ahead and click new notebook. What's really nice about this is this right away in our input directory, we go ahead and we already have the dataset loaded in. So you can see the JSON files and the image files. I'm going to go ahead and remove this first cell. Okay, so if you followed along in the deep learning framework videos that I built, I kind of built up this generic framework that can be used for training models for different tasks. Today we're going to leverage some of that code. We have to manipulate it slightly just because the nature of working on Kaggle, some of the data sets and stuff are set up differently than how I would do them myself on my own machine. If I had more control over the environment and the situation, right? So I'm going to walk you through how to make kind of those minor adjustments and how to use some of that framework to go ahead and train this model. So go ahead and import our libraries. Okay, so go ahead and importing our layers that we're going to use. So first off, we imported OS because we're going to be manipulating the files in the file system. We're going to be using CV2 or OpenCV Python for reading in our images and manipulating our images. And then we're going to be using JSON because we have JSON files for our masks. And then we're going to go ahead and use image and image draw from the pill library to basically take these JSON files and turn them into actual image masks. Matplotlib we're going to for plotting and looking at things. Partial again for any partial functions we might need to map. And then of course TensorFlow layers for the layers to build up our model. Okay, so, and then also we're going to go ahead and import date time, do some time stamping on our models, and then import pandas as we're going to be reading some of the data into pandas data frames, right? So, okay, so I'm not going to actually walk through coding up the entire UNet. if you would like to see the finer details of that, you can go ahead and go back to my previous video and watch that. So what I'm going to do is I'm going to copy and paste it in. Maybe give a brief highlight again. We have our convolutional block, which has our convolutional layers and our activation functions and dropout. Oh, I misspelled that, but that's okay. We don't need it. So one second here. There we go. Okay, so again, we have our activation functions, our dropout, and our convolutional layers. We have our encoder block, which takes the convolutional block, passes the inputs through the convolutional block, and then performs some sort of pooling operation. Here we're going to be using max pooling. Our decoder block is what's going to bring our deep global features back up to a higher spatial footprint, right? So we're going to actually perform upsampling, so convolutional 2D transpose, and then we're going to add them together and pass again through another convolutional block. And then we have, so now we have kind of our bigger modules here, right? So our encoder block and decoder blocks, and we'll go ahead and build our UNet model, which takes an input image, and then it passes it through our encoder blocks until we get to some deep global feature space, which is here, the bridge. And then we pass each of these skip connections from the encoder blocks, as well as the deeper feature spaces back through the decoder blocks until we get our output, right? So here we, again, if we have a number of classes, which we will for this equals to 2, right? It's a binary classification problem. Then we're going to use the sigmoid activation. And then if it were anything greater than that, some sort of multi-class problem, we would use the softmax. So go ahead and load our UNet model. So now we have that functionality. And then the next thing we're going to do is we're actually going to pip install a library. So what's kind of neat about this particular library is it's called segmentation models. So I'm going to go ahead and use the exclamation point, pip install. Segmentation models. And what this allows us to do is allows us to, we could write our own loss functions in our own Python function, but it's much simpler just to import them from an already an easily installable library such as segmentation models. Also, if you don't want to use this particular code for your UNet model or your segmentation models themselves, if you go into their docs, which I can leave a link in the description, you can use either a UNet model with already pre-trained ImageNet weights in it, or you can use, I think they have a couple other different architectures like LinkNet or some other similar architectures that are used for semantic segmentation that you can try out and load in directly from the library. So I basically kind of like to code up my own just for not necessarily because I'm not trying to necessarily build state-of-the-art systems. It's more so I have a better understanding of what's going on underneath the hood, right? So later when you get to more complicated tasks and situations where you can't use pip installable models, then you actually understand, what are the building blocks to that model? What makes up these things, right? So it's kind of why I use that, especially for some of these toy problems where it's more for learning and fun than it is for any sort of actual deployable system, right? So, okay, now that we've installed that library, we can go ahead and import a few things. So I've already kind of written this out. So we're going to import segmentation models as SM. And then we're going to import our metric, which is going to be IOU score. And then we're going to import some of these loss functions. So we're actually going to be using, I think, binary focal Jacquard loss, but here's a couple of the other ones. Again, if you go through the docs, you can go ahead and look at all the loss functions and metrics that are offered by this particular library. Okay, so the next thing I would like to do is I would like to define a couple functions so that we can go ahead and take a look at this data, right? One of the first things you need to do in any sort of problem is understand the main objective, right? So the main objective is we need an image and then a per pixel mask to be sent to our model to get some sort of output, right? So in order to get to that, then we need to go ahead and look, we understand the objective. Now we need to go ahead and look at our data, right? So how do we get our data from how it is and how it's stored to that expected input style or format, and then get it to our model and then get our outputs, right? So as we can see here, we have JSON files. These aren't images, right? It's from our mask. So let's go ahead and take a look at some of those JSON files just to see what's going on and try to brainstorm ideas on how we can generate some images from them, right? So I'm gonna go ahead and define a couple functions here, and then I'll explain. Okay, so here I defined two functions, one to read in our images, another one to read in our JSON files. So basically what we're gonna do is we're gonna read our image in, we're gonna convert the color from, because OpenCV reads them in as a blue, green, red, we're gonna convert it to an RGB format, so that when we plot them, they actually have true color to them, they don't look weird. And then we're gonna return our image as a float, and then we're also going to divide it by 225. So what this does is it normalizes the image so that each pixel value ranges between 0 and 1 instead of 0 and 255, 255 being the maximum RGB value. And then read JSON, so basically we're just going to open up our file and load it into a Python dictionary. So let's go ahead and do that. So we're going to go ahead and look over here. We're going to copy this path, paste it. So and then we're going to go ahead and just pick that first one. So that's going to be our mask path. And then we're going to make our image path the same thing, except for it's going to be PNG. Okay, so mask, we're going to go ahead and read JSON of our mask path and take a look at what we got. Okay, so you can kind of look here, right? So maybe a good way to start here is just to print out the keys. So we have version, flags, shapes, line color, fill color, image path, image data, image height, image width. So these are just kind of the attributes in this file. The one thing we kind of want to look at is we want to look, if you want to access any of these attributes, you just access them like a Python dictionary, because that's really what it is. And then let's go ahead and take a look. So mask, we go ahead and look at the shapes. So what this is kind of telling me is that there's an array, right? An array for this image, and there at these particular points, this is where they say that there's a human in the image, right? So because this is a polygon, so if we can somehow impose these points onto, initialize an array of zeros in the correct shape, right? Shape of the image and of this mask, and then impose these points over the array, then that can generate our mask, and that will be what we can use for training our model. Okay, so what we're going to do then is we're going to go ahead and give me one moment. We're going to go ahead and move forward here in a minute. Okay, so now that we have our read JSON and read image functions kind of working, the next thing we want to do is go ahead and actually build up a function that turns this JSON data into an actual image array, right, with our points imposed over it. So actually what I'm going to do is I'm going to go ahead and change this to data equals read JSON mask path, and then go ahead and run here, right? So look at our mask. Oh, actually, no, sorry, our data.keys. So go ahead and rerun these. Oh, go ahead and call that, right? So go ahead and take a look. So here we have our shapes, our image height, and our image width, right? So what I'm going to do is I'm actually going to define a function called read mask. So what this is going to do is it's actually going to read the JSON data into a mask, which is a NumPy array of the correct shape, which we can then use for our final training. So what we're going to do here is, again, we're going to pass it the data. So I'm going to go ahead and type out a few things, and then I'll kind of walk you through what's going on. Okay, so to kind of walk you through what's going on here with this function. So basically what we're doing is we're initializing our mask as a new image, and we want it to be of the image width and then also the image height of the data, and we want to fill it with a bunch of zeros, right? So the next thing we want to do is we want to go ahead and create a draw object so that we can draw polygons onto that image. So then once we create that draw object, then we pass it a polygon, and here I'm actually basically converting the list of points into a list of tuples. So if that's all I'm actually doing here for the this for loop here. So if we go ahead and actually just take a look, at data shapes, you can see, so the points are basically a list of lists, and what this particular function requires is that they be tuples. So that's where we go ahead and make that adjustment, and then we're going to go ahead and fill that with ones, and then we're going to return it as a NumPy array, float 32, which is what our model will expect. So now that we kind of have that, the next thing we kind of want to do is we need to go ahead and just take a look. So take a look and make sure that our functions are working properly. So go ahead and call our read image on our image path, and then go ahead and read mask. I'm actually going to change this here to data, and then we go ahead and take a look at the shapes. So we have our image shape is obviously 960 by 540 by 3 because it's a three channel image, and then we have our mask shape which lines up properly. And then we're going to go ahead and call our plotting functions. So basically, in order to just kind of look at these, we go ahead and call plt.imageShow, pass our image. PLT is from matplotlib.pyplot. And then we go ahead and see, like, yep, there we go. We have, it looks like an image and a mask where it's outlining the woman in this picture. Looks to be doing quite well. So we know that our image functions work, and our read functions for image and mask work. So the next kind of thing we need to tackle, though, is we go ahead and look at the size and the shape of this image. One thing, if you remember correctly, and you know about UNet or semantic segmentation or encoder decoder type models, is that they require images that are passed to them that have like symmetrical symmetrical size of the sides, right? So you want to, if you're going to need to have something like 128 by 128, 256 by 256, something in that nature. Also, if we go ahead and actually take a look at all of our data, we'll be able to see that everything, all of the we'll be able to see that all of these images kind of all have different sizes themselves. So let's go ahead and take a look. Sorry, I'm going to go ahead and grab this path. So basically what I'm doing here is just iterating through the directory, and if the file ends in PNG, I want to append it to this list so that I can get all of the image paths. So go ahead and take a look. So there we have them. And then what I'm going to do is I'm going to go ahead and create another list. Yeah, we'll just go ahead and initialize another list. So for file in image paths, basically what we're going to do is we're going to go image equals read image file, and then we're going to go ahead shape.append image.shape. Go ahead and let that run, and then we'll go ahead and call shape. So basically what I'm doing right now is I'm going to iterate through all of the images in the file in the directory just to kind of get an idea of, you know, what are the different shapes. So we can kind of just, something you should do is you should kind of analyze the data you're working with to get an idea of like, well, you know, what are the smallest sizes, what are the largest sizes, is everything uniform, are things not, you know, so that you can kind of prune and kind of figure out, you know, which ones you want to use for actual training data. So as you can see here, we have lots of different sizes. So kind of what I suspected and kind of what I've already knew. So we're going to go ahead and handle that in our functionality before we actually get to the model. All right, so like we just kind of discussed, we kind of need to apply some pre-processing steps. So we're going to go ahead and define a pre-processing function. So what we're going to end up passing to this function is our image path, our mask path, and then our config. So if you kind of remember from the framework videos, or if you haven't seen them, I talk pretty heavily on why I like to use config files and how I use them in some of my different functions when I'm building up kind of these workflows. So we'll go ahead and define the sub function. So basically why there's a sub function is because we're performing NumPy operations. So then what we're going to end up doing is passing this NumPy function as a TensorFlow NumPy function to the data. You'll kind of see that's kind of why there's, you know, kind of these sub functions and why it's built out this specific way. It's just because some of the nature of dealing with tensors and trying to pass and do certain NumPy operations on tensors and TensorFlow gets to be a bit tricky. Okay, so basically the sub function, all it's doing is it's decoding our image path from a binary format, which happens when we create our TensorFlow datasets, decoding them and then passing it to our read image function. Here we're decoding our mask path, passing it to our read JSON function to get our data, and then passing that JSON data to our read mask function. So the next thing we're going to have to do is, like we were just talking about, is everything, all the images seem to be different sizes. So what we're going to do is go ahead and resize them. The reason I like to use the config for setting my shape is because sometimes, I like to experiment with resizing my images and masks to different shapes, and it's a lot easier to pass and go and change one parameter in your config file than it is to go through all your code and try to figure out where you have the shape set and make sure that you get everything done properly. So it's kind of why I like to do it that way. Also, if I haven't really said it yet, one of the reasons why I'm using this Kaggle notebook is because you actually have access to free GPU usage. So if it's something you don't have on your own machine, it's really useful to have GPUs when performing any sort of training any sort of image models. It speeds things up a lot, and it's actually kind of unreasonable to try to do any sort of image processing on a CPUs. So it's kind of nice. You can either use Google Colab or anything like that, but I like to use Kaggle just because the data set was here, so it's easy enough to get the notebook going right where the data is. Okay, and then we need to expand the dimensions. So basically TensorFlow expects this to be in like a 256 by 256 by 1 because it's that's the shape of the final channel. So we're going to go ahead and expand the dimensions, and then we're going to go ahead and return the image dot as type numpy float 32, and then mask the same. So that's kind of our sub numpy function. So the next thing we're going to do is in our pre-processing function, apply that. So tf numpy function, we're going to pass f, which is this. As the parameters, we're going to be passing image path and mask path. And then for the output data formats, we want them to be in TensorFlow floats. Now we're going to go ahead and I'm pretty sure it's when you're running things in eager execution and requires shapes to actually be set. So what we're going to go ahead and do here is pass the shape to set the image as, and then same for the mask. We're going to go ahead and set the mask. Again, all kind of from the config file to keep things simple, keep things easy to change as you go. And then finally, we're going to return our images and masks. So there we go. So now we have our pre-processing function. What we're going to do next is we're going to go ahead and build up our TensorFlow dataset function. So I've kind of covered this before, so I'm just going to kind of copy and paste it in here, and I'll kind of walk through it. So basically what you're going to do is you're going to read in two arrays or lists basically from tensor slices, right? So we have our X and Y, which is our image and our mask paths. We're going to create a data set from those tensor slices. What we're going to do is we're going to go ahead and shuffle them. The reason you want to shuffle them, right, is because we're going to be batching them up. So if you were to use like actual gradient descent, stochastic gradient descent, what would happen is it would pull one sample from the training data set, compute the loss, update the gradients, and then continue to iterate forward like that, right? So the problem with that is it's extremely slow. So in order to deal with that and make it faster, we make some assumptions about our training data, the assumptions being that it's all similar enough that if we were to take batches of it, compute our loss, update the gradients across the average loss of the batch, that since the training data is similar enough, the gradient updates will still be in the right direction. There won't be any sort of confusion. So that's kind of the idea behind it, and it speeds up our computation, and then it also allows for different kinds of things. So that's kind of where the batch kind of comes from, and then again, kind of for the shuffle, right? You don't want to at the end of each epoch. So one whole epoch of training is the model sees the entire training data set. At the end of that, you don't necessarily want to feed the data, feed the model the data in the same order again, and you also don't necessarily want it all to be batched in the same batches again. So what you do is you shuffle things so that the next time, the next epoch happens, not only are your data augmentations like your flips and shifts and zooms and all that and crops happening, but you're also not sending the data in the same order and in the same batches as before. Again, these things are done to prevent things like overfitting, or at least to make it harder for the model to overfit onto certain things. So now that we've kind of shuffled our tensors, then what we go ahead and do is we go ahead and map our preprocess. So again, kind of the reason why I'm using mapping our preprocessing function here is because we're using images. So basically my tensors are just image paths, and then we're batching it up and then mapping the preprocessing function. So then we're only reading into memory batches of data, because if you're reading the whole data set, especially once you get into large data sets, right, you got terabytes of data, you're not going to have enough room in memory on your GPUs to read in all of the data at once. So that's kind of where this batch and map and shuffle mentality kind of comes from, especially when you're doing image tasks, right? Stuff where you're having to read in batches of images. You can fill up memory really quickly, and you'll run out of memory and not be able to train on the GPUs. So, and then if we are training, I want to apply my augmentation, and then again prefetch. So the prefetch is happening so that while the GPUs are computing the loss and updating the gradients, the CPUs can be pulling in and loading in more data, applying the map function, right, loading them into memory so that the GPUs don't sit stagnant, not actually operating on anything. And then go ahead and auto shard policy as data, right? So there we go. We have our TensorFlow dataset function. So the next thing I want to do is I kind of want to walk through the augmentation. So there's lots of different augmentation you can apply. In this video, I'm basically just kind of covering the data processing portion of this whole workflow, and then in the next video we'll get into training and then actual deploying it to some kind of like real world, making some kind of solution to where you can use this trained model now to do some other things. So what I'm going to do is go ahead and jump into the augmentation and some simple simple augmentation techniques you can use for semantic segmentation tasks. So I'm going to go ahead and create a class by subclassing, class called augment, subclassing keras.layers.layer. I'm going to go ahead and initialize this class. And then I'm going to set seed, which is going to be our random seed, to equals to 42. Okay, and then I'm going to create these functions. So self.augment, inputs. Okay, so here you can see all the different types of augmentations. What we're going to go ahead and do is go ahead with random flip mode equals horizontal and vertical, because we want horizontal and vertical flipping. And then what we're going to do is go ahead and set the seed. So that way when we're applying this transformation to now the labels, which is going to be the same function, we're going to make sure that the same exact transformation is happening so that they're not being mixed up. And then we're going to create another one, which we're going to do is called zoom. This one's actually not random flip though. This one is random zoom. And we're going to give it the scale of 0.3, 0.2. These are kind of arbitrary. You can kind of mess with this to see what, if anything makes a difference, makes better or worse. We're going to go ahead and have fill mode constant. And then we want our fill value equal to 0.0. And then again, we want to set our seed equal to the seed. So basically that's kind of initializing our class functions. And then what we're going to do then is we also need to define the call function. So what happens when this is actually called? So self inputs and then labels. So we're going to go ahead and do the random flipping, and then we're also going to go ahead and apply the zoom. And then we're going to go ahead and return our inputs and labels. I see I for sure at least have one typo. I probably have more. Go ahead, and there we go. So that kind of sums up at least kind of the augmentation portion of it. So you can go ahead and define any of your own augmentation class and any other augmentation techniques you want to do. Just kind of follow the same kind of format. So for the next part and the final portion of at least this part of the kind of mini series I'm doing on this problem, what we're going to do is we're actually going to generate our tensors from this directory. So we're going to go ahead and define the root directory, which is input Okay, so next thing we need our paths. The thing is we want the core path for both the image and the mask. So we're going to go ahead and do that in this way. Want to pass the root folder and then file, and then we want to get everything except for that last 4, which is going to be either the .png or the .json. For file in root. So go ahead and pass set. So for the set of the files in that list directory. Oh no, maybe that doesn't work. Maybe that logic doesn't work. Let's just go ahead and do this. So that we're only calling each thing once, we're going to go ahead and call this. And there we go. So if basically just calling in all the image files and then removing the .png so that we can replace that with .json if need be. So the next thing we need to do is we need to split these things up, these paths up into an 80-20 split, or whatever split you want to use for training and validation. So I'm going to go ahead and define a function for that. So samples and then %, and then so basically we're going to get a list of indexes. We're going to set a seed so that it's replicable. We can repeat it. And then we're going to shuffle that index so that obviously we're not pulling from, we don't want two examples that are next to each other. We want to shuffle things up. And then the next part we're going to do is we're going to define our train index, which is going to be the first 80%. And then our validation index, which is going to be the last 20%. Or whatever percent you use. And what we're going to do is return those. and there's your index grabbing function. So basically the only thing we need to do then is call that function. So here's where you pass the percentage you want to use. I want to use 80%, so I use 0.8. So basically, in order to index these lists, I convert them into NumPy arrays. And then here I pass the train index and then the validation index. So now these should be our train paths. So I called something incorrectly. Oh, here we go. Okay, so now to get our actual train images, and there we have it. So now we have our train images, our train masks, and then also the same for our validation. So now we have actually built up our tensors that are going to be sent to our TensorFlow dataset functions to build up our TensorFlow datasets, which is then going to be sent to our model for training. So basically, that's kind of the gist, at least, of getting the model and analyzing and getting things into the correct format. So basically now we have functionality to build up our tensor slices. We have functionality to process those tensor slices into actual NumPy arrays that can be read into batches that are sent to the model for training. In the next video, I'm going to go ahead and walk through how to set up the actual training workflow and actually expand upon. Now we have the data working properly. Let's go ahead and walk through how to get the model training up and going. So I hope you enjoyed. I hope you got something meaningful out of it, and I'll see you in the next one.